In this tutorial, we will discuss how to provide the plastic hinges to the shear wall. So plastic hinges are required to define the material nonlinearity to the structural element. So this nonlinearity, that is a material nonlinearity. So this is required to assign each primary element like a column, beam, and shear wall to perform the nonlinear analysis like pushover analysis and time history analysis. So in this particular tutorial, we'll discuss about the how to define the nonlinearity to the or plastic hinges to the shear wall. Now, there are different approaches to assign the material nonlinearity to the shear wall. So one of the approaches is that the shear wall is modeled as a wide column. It is modeled as a wide column, and then assign the material nonlinearity to that wide column just like a regular RCC column. So this is the simplest approach of assigning the material nonlinearity to the shear wall. Okay, now we'll follow that particular approach. On screen, you are seeing one RCC building G+4 structure, and already columns and beams are there, and the slab is also there, and the different loads are already applied on this particular model. Now we will assume that, or we will provide the shear wall in between, in middle bay. Okay, so the size of the bay is width is equals to 5 meter, and the height is equals to 3.1 meter. Story height is 3.1 meter. Okay, now we will follow or will use a wide column approach to assign the shear wall. Okay, so how to do this modeling? So first of all, define section property and frame section. Okay, then here in this add new property. So it is a concrete rectangle. So the section name as a wide column. It is as a wide column. Okay, then depth of the section, depth in the sense thickness of the section. Okay, so the thickness of the section is say 200. So as per IS 13920, minimum thickness of the shear wall is a 200 millimeters. So therefore, in this case, this depth of wide column we will assume as a 200 millimeter, that is 0.2 meter, and width is equals to width of the bay, so that is equals to 5 meter. Okay, so this is our, now instead of calling as a shear wall, it is called as a column, and since the length of the column is more, it is 5 meter is there, therefore we are calling this as a wide column. So the column dimension is 5 meter by thickness is 200 millimeter. Okay, then material, concrete material, say it is M30 grade. Now we'll see about the reinforcement in the wide column. So it is a concrete. Okay, so that is reinforcement, concrete reinforcement. So longitudinal bars. Okay, so it is a that is FE 415 grade. Confinement bars, the grade is also HYSD 415. Okay, now it is a wide column. Therefore, design type is first. Design type is the first, that is column PM2 M3 design. Okay, then reinforcement configuration. Okay, so here this is a column, wide column having length equal to 5 meter. Okay, now we will provide the reinforcement like this. So these are the vertical reinforcement in the wide column. It is wide column, and this is, we will provide the reinforcement in both the faces, and let this spacing will be equal to 150 millimeter. So this configuration is a rectangular configuration, so therefore the first option is a correct. Okay, then confinement bars we will provide as a lateral ties. Okay, so that is confinement is a lateral ties. Next, longitudinal bars. Okay, rectangular configuration. Now clear cover, this clear cover for the confinement bars. So how much cover is there? So we'll provide the cover as a 15 millimeter. So 15 millimeter, that is 0.015 millimeter. Then number of longitudinal bars in direction 3 and number of longitudinal bars in direction 2. Now this and this we have to. Now number of bars in the longitudinal directions. Now here we are seeing the figure. Okay, so two direction, so three direction means this. This is direction 3. So this is a 3 directions. Okay, now in 3 direction, in direction 3, okay, so how many number of bars? That is when we take the section here. Okay, how many bars we are seeing from this? 1, 2, 3, 4. So these bars are there. So this length is equals to, this length is 5000 or 5 meter, that is 5000 mm is the length, right? So this is the length, and spacing is equals to 150 center to center, 150 center to center. So therefore, how many number of bars is coming? So it is equals to, it is equals to 5000 divided by 5000 divided by 150 is the spacing. So how many number of bars it is? 33. So roughly we will select a round figure as a 32 number of bars. Okay, so it is a 32 number of bars. So here first, this is a 32 number of bars. Okay, then number of bars in the longitudinal, the number of longitudinal bars along direction 2, that is second, in 2 direction. Okay, so here this is our configuration, this is our shear wall. So these are the bars in this side and these are the bars in the opposite side. Okay, now this is a 3 direction. Now 2 direction is this, 2 direction is this, this is the direction 2. Okay, now in this direction, how many bars are there? Now these bars are providing 2 layers. Okay, so first layer will be in this side and second layer will be in this side. So in the 2 direction, there are 2 number of bars. So 2 number of bars, it means there are 2 layers. There are 2 layers. There are 2 layers. Okay, so this is most important to define the reinforcement in the longitudinal 3 direction and longitudinal 2 direction. Okay, so this is direction 3 and this is direction 2. Okay, next. Then about the bar diameter. Okay, longitudinal bar diameter. So let it is equals to 10 millimeter. Okay, so it is a 10 diameter. Then next is confinement bar. What is the size? Confinement bar, minimum bar diameter for the confinement as per IS 13920, it is 8D. Okay, spacing of confinement bars. So whatever the lateral ties to be provided to the white column, the spacing, let it be equals to 0.125. So that is 125 center to center, 125 center to center. Then number of confinement bars in 3 direction and 2 direction. Okay, so I will explain here. Okay, now see, this is for example shear wall. This is wide column, for example. These are the reinforcement in 3 directions. So these are the 32 bars at a spacing 150 center to center. Okay. Okay. Now confinement bars, let me provide the confinement bars like this. This is a lateral ties configuration. Lateral ties configuration. Okay. Then since the length is more, so therefore we will add one more here also. That is in this way. In this. Okay. Now we'll fix up our configuration like this. Okay. Now first is number of confinement bars in 3 direction. Now 3 direction is this. This is the 3 direction. Okay. Now take the section. Take the section along 3 direction, and it is cutting how many number of lateral ties. Okay. So it is 1. This is first, second, third, and fourth. So in 3 direction, here will be 4. This will be 4. And number of confinement in 2 direction. Now 2 direction is this. This is the 2 direction. Okay. Now in 2 direction, it is cutting how many bars? 1 and 2. Only 2 lateral ties are has been cut. So here it will be 2. Okay. So here first of all 1, 2, 3, 4. So this is 4 and this is equals to 2. Okay. And then so check the design. So we'll go for the second, reinforcement to be designed, because whatever the reinforcement we have provided, So it is provided randomly. We have not designed. So therefore, go for second, design reinforcement to be designed and say okay. Okay, now the reinforcement in the wide column have been defined. Okay, now in this way, first of all, define the frame section as a wide column. Okay, then so this is a wide column. Okay, and now we will provide the wide column here in between in the middle bay. Okay, so here in between in the middle bay we will add one more grid line. Okay, so this is A, B, this is C, and this is D. We will add one more here at the center. So that grid line will equal to say DE. Okay, or whatever the next name. So how to add the grid line? Why it is required? I will explain. So first is coordinate system grid. Okay, then modify the grid. Okay. So already there is A, B, C, D. Now I will add one more, that is E. Okay, that is E. And how much this distance? So first, now see, this is the first grid line. This is A grid line. So it is 0. Okay, so this is coordinate. Okay, so this is the origin of the coordinate system. So this is 0, then this is 5 meter, then this is 10 meter, and next grid line D as a 15 meter. Okay, now here we will provide grid line middle. So what is the distance? 0, 5, and then 2.5. So it is a 7.5. Okay, so this distance will be equal to 7.5 from the origin. Okay, so here E grid line is equals to 7.5 meter, and just say okay, then it is okay. Okay, now this is a grid line, right? So we have added a one more grid line, and then we will assign the wide column here along the center. So just like a regular column, how we assign, in that way, assign the wide column at this center grid E. So take this command as a link command. Okay, then here it is a wide column. Okay, already it is defined. So just a click here, and it should be up to the end. Okay, so this is a wide column we have assigned. Okay, then this is a wide column, so it has a support. So at the base, provide the support. So here, so we can provide fixed support, so we can provide the pin support. So in this case, we will provide the pin support. So just select the bottom end of this wide column, and then assign joint restraint, and this is a pin connection. Okay, so pin connection, apply, and okay. Okay, so do not forget to assign the support to the wide column. And now we have defined this particular the shear wall as a wide column. Now we'll see the extrude view. Okay, thick section, we'll make it as a thick section, whether assignment is done correctly or not. So for that, here the command display option is there. So this is a set display option, and then here go for general option, and then it is extrude view. See extrude view, and then apply and okay. Okay. Now, is it now we'll see the 3D view also. We'll 3D view. Okay. Now we'll rotate also. Okay. Now is it provided? Is it assigned properly? No, it is not assigned properly. Okay. So what actually happened? So the shear wall 5 meter. So it is assigned not in the bay direction, but it is perpendicular to bay direction. So therefore it is required to turn the shear wall. It is required to turn it. So go for XZ column. Okay. So this is actually it is required to turn it. Okay, so how to turn it? So select the element. Select the element completely. Okay, and then here assign frame and local axis. Assign frame, local axis. Okay, and then here angle from default orientation. So it is turn it to 90 degree. Turn it to 90 degree, and then see what the magic happens here into the model. Apply and okay. Now it is turned. Now shear wall is turned. Now this is wide column as a shear wall we are seeing. Okay. Now this is about definition of the shear wall as a wide column. Okay, and then assign the nonlinearity to this particular this wide column, just like a regular RCC column. Okay, so in SAP 2000 there are ready-made atto hinges, plastic hinges are there. So we'll assign the same hinges to this particular shear wall or wide column. Okay, so we'll remove the exclude view of this. So we will make as a standard view, apply and okay. Apply. Okay. So these arrows, whatever you are seeing on each structural element, so these are nothing but the local axis or axis of each element, and this is called as the local axis. Okay, so just hide this axis. So click on here, set show undeformed shape. Okay, so now we will assign the flexural plastic hinge to this particular shear wall. So just select all, that is select the wide column. Okay, select wide column, then assign frame, and then here it is hinges, assign frame hinges. Okay, okay. Then in the column, so this is a column. So we assign the nonlinearity here at this end, and we assign the nonlinearity to the here. So this distance, this is a say 0.1, this is 0.1, and this is 0.9. So these are the two locations. So we usually assign the plastic hinges near to the end. Okay, so first relative distance is, so this is 0, this is 0 beginning, and this is 1. So we will assign the first plastic hinge slightly below the starting point. So at a relative distance equal to 0.1, and next hinge in the other end, bottom end, so at a relative distance equal to 0.9. Okay, so therefore first is 0.1. Okay, 0.1 relative distance, add hinge. Then so this, it is a ready-made hinge or atto hinge, and so atto hinge in the sense it has some parameters. There are some parameters are there. So these parameters are taken from ASCE 41 2017 code. It is American code, and therefore SAP directly extract the values required to estimate the properties of the plastic hinge from this particular the table given in this particular code. Okay, then select the type of the member. So it is a select a hinge table. So these tables are given in ASCE 41 this thing. So this table for now this is a search for concrete column. So it is a concrete column. So it is table number 10.8 and 10.9. These are the two columns. These are the two tables are there for this particular in ASCE 41 related with the properties of the hinges for the columns. Then degree of freedom. Okay, so degree of freedom. So column is a PM to M3 degree. So select a PM to M3 degree. Then now to estimate the hinge properties, the axial force values are required. So axial force value, so the software is asking that whether the software will automatically take the values from the analysis or user want to specify the values. Okay, so the two options are there. Now we'll select the first option, that is case and combination. So for this particular model, already the gravity load case have been defined. Okay, so what is gravity load? On the structure, the dead load plus live loads are there, plus a floor finish weight is there, then weight of the walls. These are the permanently acting gravity loads. So these are already defined in the model. So therefore, so here it is, so it has come here as a dead load gravity. So we are giving instruction to the program that whatever the p value required, okay, so to calculate the p value, so use the dead load and that is gravity and gravity lateral load cases. Okay, so then automatically the program takes the value from these two load combinations. Then next is to calculate this thing, the shear value, shear force value is also required. Now see, we are assigning the hinge, this particular hinge at a relative distance 0.1. So what is the shear force value? What is the shear force value? So first option is a program calculated. So that is the program automatically calculates the shear force and it takes here for the calculation of the properties, or the user also can define his own values. Suppose there are some, you have some formula to calculate the shear force. Then in that case, go for the second option. Now we'll go for select for the first, program calculated. So select the first one, program calculated. And next is a shear reinforcement ratio. So again, there is one ratio is there, that is shear reinforcement ratio is AV. Okay, area of vertical stirrups divided by BW plus spacing S. Okay, so again, so from the current design, that is software automatically extract the required ratio from the design of this. This building is already designed, so not necessary to do the much calculation for this. So this is the beauty of the auto hinge. So the user need not necessary to do any type of calculation. So you just appropriately select these particular options and then this. So provided that this, whatever the building, whatever this building to which the shear wall nonlinearity to be defined. So in that case, it must be designed first. For seismic loading, it must be designed. And once the design is completed, then all the results are there in the program, in the this thing, in this particular case, all the results are there. Then at required time, it will take the values from the analysis. Then this is, let it be default values. Then say okay. Okay, so we have defined the first hinge, plastic hinge at a relative distance equal to 0.1. Okay, then next is at 0.9, we'll define the another hinge at the bottom 0.9. Okay, so here again click. So the same properties has come, whatever the properties or whatever the parameter we have chosen for 0.1 location. So just okay, just okay. Okay, so the two hinges have been defined and say okay, apply, sir, apply and okay, apply, okay. Okay, now it is showing the hinges to the other elements also, beams and columns, and to these particular elements already this model is already analyzed for pushover and time history analysis. So therefore already to the columns and beams the nonlinear hinges have been assigned, and it is also so these hinges are so already defined hinges are there. Okay, now we are interested about this. Now this is about a wide column. This is about the wide column, and you are seeing these are the rightly this thing assign the hinges here. So these are the hinges. Okay, now the assignment of the hinges, plastic hinges to the shear wall part is over. Then we can do the type of the analysis, whatever the nonlinear analysis, pushover or time history analysis. Okay, so that is we can see in 3D view also. In 3D view also. Okay, so we are seeing that so the nonlinearity to each element, column, beams, and the shear wall is also provided. So therefore, after this, so this step is very important of assignment of plastic hinges of all this structure element, and then go for the pushover time history analysis. Okay, so now this is the objective of this particular tutorial. That is, in this tutorial, I want to just explain how to assign the nonlinearity or plastic hinges to the shear wall. And we have seen that the shear wall is modeled as a wide column, and this is the simplest approach. Second approach is also there to assign the material nonlinearity to the shear wall. So in that approach, the shear wall is modeled as a shell element. It is modeled as a shell element, and then in that multi-layer shell one option is there. Okay, so multi-layer shell using this particular approach, the nonlinearity also we can assign. So that particular option is inbuilt in SAP 2000. Okay, in SAP 2000, and you will find the procedure how to assign the material nonlinearity using this multi-layer shell element on a Google also. In a Google, you just type it. Okay, so that is a multi-layer shell element in SAP 2000. So you will get the one YouTube video, and in that you just see it. Okay, so you will watch the video, you will understand how to assign that particular nonlinearity by using that particular approach. But thing is that about the shear wall, you that is either assign the nonlinearity by using wide column approach, what is called a lumped plasticity approach, or by using a shell element that is called as a distributed plasticity approach. So both options gives the researchers have been studied these particular cases, and then they have the result shows that by both the options we are getting the results very close to each other. So my personal this thing is also there, suggestion is that, so whenever the shear wall nonlinearity point comes, so in that case, so you always go for the as a wide column approach. It is